So I clicked record. Don't forget we have a lab this Tuesday, today at 2 o'clock. I'll probably be there by 1:30, 1:45 for those of you that want to get there a little early and finish up the lab. I think it's pretty straightforward lab. I think Monday the last group was gone at around 2:45, 2:50. Okay, but actually there was most of the lab groups were done in 20 minutes, as I predicted and as I expected. Okay, so, and also don't forget for this lab on density of solids, I'm not going to cover it on the exam, I'm not covering it in lecture, but you can use the lab report, the lab handouts and whatnot to help you do and complete that lab report. All right. All right, so let's get started here. So we left off last week talking about colligative properties. So can anyone name some of the four colligative properties?
Vapor pressure lowering.
Very good. Okay, we did a problem last week on vapor pressure lowering. Okay, what else? We're going to do a problem like this just right now. Very good. The boiling point goes up, and what happens to the freezing point? Goes down. Okay, this is when you add a solute to a solvent and everything dissolves. And then we have osmotic pressure. Okay, so these are the four colligative properties. So let's do a problem involving two of these four, and that is the boiling point goes up and the freezing point goes down. Okay, what is the boiling point and freezing point of 478 grams of ethylene glycol and 3,202 grams of water? The molecular weight of ethylene glycol is 62.07 grams per mole. So a similar question like this will be on your exam. I think it's also on the study sheet for Thursday. So let's draw this out here. We have water. Okay, we got 3,202 grams or so of water. Okay, and what is the boiling point of water? We know this as 100 degrees C. What is its freezing point? Okay, we know this as 0 degrees C. That's correct. Okay, and now we're going to take that same 3,000 grams or so of water. 3,000. Okay, and to that we will add how much? 478 grams of ethylene glycol. So the question here is, what is our new boiling point? And what is our new freezing point as a result of adding 478 grams of ethylene glycol? So what is the solute in this situation? Okay, the solute is going to be water. Okay, always will be water. Okay. And what will our solute be? Okay, our solute is going to be ethylene glycol. And our solvent is always water, okay? At least for this class. All right, so the equation we're going to use is this. The new boiling point, or the change in boiling point, is going to be Kb, a constant, so I'll give you that on the exam, times the molality. Molality. So what is molality? Okay, it's a type of concentration, but what does it mean? Okay, it's, anybody want to say? Do you know what molality is? Bailey? Molality? It's
I believe it was moles divided by...
Moles of what?
Moles of solvent divided by...
Not solvent.
Solute divided by kilogram solvent.
That's correct.
There we go.
Okay. So this is also known as molality. Molality. Not molarity, but molality. So this Kb is a constant, and let's look at that constant here. So I'll give you that. Okay, our solvent is water. So what is Kb for water as our solvent? 0.052 degrees C over molal. Yes, sir. Okay. Jacob. 0.52 degrees C over molal. So this is just plug and play. Okay. Actually, moles of solute, right? So let's convert that into moles of solute. So 1 mole of ethylene glycol goes into 62.07 grams. Okay. So 478 divided by 62.07. What is that on our calculator? About 7.701 moles of ethylene glycol. And what is our kilogram of solvent? For that, we can just move the decimal places 3 to the left. Okay, so this will make it 3.202 kilograms. So Kb, like I think Jacob mentioned before, is 0.52 degrees C over molal. Okay, I'll give you that constant on the exam. Times moles of solute, which is 7.701 moles. The molal and molal cancel. See, this is moles over kilogram cancel. So what's 0.52 times 7.07 divided by 3.202? 0.52 times 7.701 divided by 3.202. 1.251 degrees C. 1.2. We'll do 1.25 degrees C. 0.25 degrees C. So this is not the answer. Okay, this is not the answer. Okay, why is this not the answer? Yes, it's the change. So what is the answer? Okay, our new boiling point will be what now? Not 1.25 degrees. Boiling point of water cannot be 1.25 degrees. So what will it be? Yes, sir. 100 degrees plus 1.25 degrees C, and we're looking at about 101.25 degrees C. Okay. So I see this in all my years here at Methodist. Students just use this as the answer, but the real answer is this. Okay. So this is degree C. All right, let's do the freezing point now, which will be exactly the same, the only difference being the constant. Okay. right, so what is Kf now? Okay, I'll give you this on the test. Okay, you don't memorize these things. Our water is solvent. The Kf is 1.86 degrees C over m. You guys see that? I'll give that to you on the test. So 1.86 degrees C over molality divided by, let's just do this for a second here. 7.701 divided by 3.202 is 2.41 molal. Okay, 2.41 molal. All right, lowercase m cancels. 1.86 times 2.41. What do you guys get?
Wait, how did you get the 2.41?
I just divided this by this to get molal.
So you don't multiply it by like the degrees Celsius thing?
I mean, here I did 0.52 times 7.701 divided by 3.202. But I just took 7.701 divided by 3.202 and got 2.41, which is 2.41 molal. So take moles divided by kilograms, and that's our molal. Molal times the constant. I got this constant from the table. And so 1.86 times 2.41, 4.48 degrees C. All right, so this is not the answer once again, because the freezing point of water is definitely not 5 degrees or 4.48 degrees C. So what's the answer? Okay, it's going to be what? 4.48 degrees C. This is, again, what students put on the exam, which is not correct. The new freezing point will be higher or lower? Okay, lower. So what will the freezing point be then? Negative 4.48 degrees C. Very good.
So the freezing point, so for we're trying to get like a new freezing point, you essentially just subtract whatever you get like from 0, and then with the boiling point you just add 100 degrees Celsius.
For water as the solvent, you'll add to the boiling point, which is 100, or you'll subtract from the freezing point, which is 0. Okay, this is for water. Okay, what if your solvent wasn't water? It'll be different. Okay, it'll be different. All right, so that is how we do that type of problem. All right, let's do another one here. A little variation on this. All right, so we got 2 grams of an unknown compound reduces the freezing point of 75 grams of benzene from 5.5 degrees C to 4.90 degrees C. What is the molar mass of the compound? Okay, so molar mass are units of molar mass or grams per mole. Okay, grams per mole. All right, so what is our solvent here? It's not water. What is our solvent? Benzene is correct, very good. And what is our solute? unknown compound of which we're trying to find the molecular weight of. So we know the freezing point goes down from 5.53 to 4.90. Freezing point's going to go down. So our delta TF will be what number? We're going to take that 5.53 degrees C and subtract 4.90 degrees C. About 0.63 degrees C. Alright, so remember our definition of molality, as Bailey mentioned, it's moles of solute over kilograms of solvent. Okay? So Jacob, right? You mentioned our solvent is benzene, which is correct. So what is that in kilograms? We move the decimal 3 to the left. Kilograms. Our moles of solute, we don't know because it's unknown. So, and then what is Kf for benzene? Let's go back to our table here. What is K of F for benzene? 5.12 degrees C over molal M. And then our delta T is 0.63 degrees. Okay, so here we're going to have moles of solute, which is unknown. Just say moles of unknown. Okay, over kilograms of solvent, which is 0.075 kilograms. Okay, so we're going to solve for a mole of unknown. All right, so you guys know how to do this math? Okay, we're going to take 0.63 degrees C times 0.075 kilograms. Just bless you. Okay, 0.63 times 0.075 divide by 5.12 degrees C.
So you get from grams to kilograms, you just move the decimal place over 2 places.
3.
To the left.
3 to the left.
Got it.
Okay, so 0.63 times 0.075 divided by 5.12. Okay, we can actually you take that lowercase m, we can put the lowercase m here too. Okay, the degree C cancel, and the kilograms cancel, so you're left with moles of unknown. Because molal is moles over kilograms, moles of solute over kilograms of solvent. All right, so our final units are moles of unknown. 0.63 times 0.075 divided by 5.12. 0.63 times 0.075 divided by 5.12. 0.00923 moles. 0.00923 moles. I'm just figuring out how much to cut off. I will just do 3 moles of unknown. So to get this problem, how will we get our molecular weight? Okay, remember our units. Our units of molecular weight are grams over moles. Grams over moles. So we have 2 grams, which is our unknown. Okay. Divided by 0.00923 moles. Okay, so this is our answer. 2 divided by 0.00923. About 217 grams per mole. 217. Okay, and this is our answer. Are you guys comfortable doing this? I think on the exam it will be more like this type of problem, as we'll see on Thursday. But just so you know, this is also a very nice way to get the molecular weight of an unknown. Okay? And I believe in the lab you'll do this in the lab. You'll do this type of calculation for your lab report next week. Right? Are there any questions or comments? All right, our last colligative property here is osmotic pressure. All right, so I'll just go ahead and give you the formula for osmotic pressure. It's pi, okay, and it's pi equals to mRT, molarity times R times temperature T. Okay, so R is 0.0821 liters. I forgot. Liters atmosphere per mole Kelvin. All right, T here is temperature. Okay, T is temperature. Okay, this is the formula for osmotic pressure. And what do you think the units of temperature should be? If our gas constant is K, what should we convert our temperature to? Kelvin. Okay, so it must be in Kelvin. Okay, and this pi is called the osmotic pressure. Right, so just so you guys know, this is osmotic pressure, and this osmotic pressure will be in the presence of a membrane. Okay. In the presence of a membrane. Okay. So let's just say we have an example here on page 14, but let's say you have a membrane, it's semi-permeable. And we have our solute. Okay, this is kind of like your plasma membrane in biology. And then we have our solvent. Okay, let's use our solvent as water, because that's our favorite solvent in Gen Chem. Imagine this is semi-permeable, which means like it allows water to go back and forth, but not the solute. So water will rush. Okay, it will rush to neutralize the solute. Okay, this whole phenomenon is called osmosis. Okay, osmotic pressure is the pressure to stop osmosis. Okay. So it's a pressure applied to stop osmosis. right, here's another example. So imagine you have a U-tube or a glass that's shaped like a U, and then we place our semi-permeable membrane here. Semi-permeable means water can go back and forth, but not your solute. Okay, and here the solute is going to be glucose. Okay, so notice, let's highlight this in pink. Notice the levels, the liquid levels. Okay, the liquid levels here and liquid levels here. Okay. Okay, so over some time, what are the levels, liquid levels? One's over here, and what about this one? Okay, what has happened? Okay, why is it uneven? Okay, because of osmosis. You see, water rushed. Okay, water rushed to neutralize the solute, in this case glucose. This is called osmosis. Okay? Osmotic pressure is the pressure. Okay, it's the pressure that you put in to stop this osmosis. And now, because of this pressure, the levels are equal. Okay? So this is the pi. Okay, so this is the osmotic pressure, the pressure that's put in to prevent this, or to prevent osmosis. Okay, and now osmosis has stopped. Okay, you guys see this? Okay, so water rushes in, you apply the pressure, you apply it, and look at the levels. Okay, now they're equal. Right, so that's the pressure that you apply, so that osmosis doesn't happen anymore. All right, so this actually happens in our cells, and I think they call it, the biology majors know this better, like hypertonic, hypotonic. Okay, right. So your plasma membrane maintains that osmotic pressure, or else water will just rush out, or water may rush in, depending on what's inside and outside of the cell. Here's another example of osmosis. Okay, so you have high pressure, low pressure, and over time, okay, the solvent is going to neutralize whatever solute here is in the solution, okay, over time. All right, let's do our final problem here in this chapter, and then I'll have some wrap-up points, and then we'll start our review. Okay, for next Tuesday's exam. So let's do a practice problem. Right, 0.263 grams of hemoglobin is in 10 milliliters of solution. The solution has an osmotic pressure, we'll call that pi, 7.51 torr at 25 degrees C. What is the molar mass of hemoglobin? So once again, molar mass, we want to say grams over mole as our final units. Grams over a mole for molar mass. Okay. And so our equation is pi equals mRT. I'll give you this equation on the exam. Okay, and I'll definitely give you R. All right, the first thing I would do here is I would take this atmospheres, and I would take this torr, which is a unit of pressure, and convert it to atmospheres. Okay, because R is in atmospheres, our constant. Right, so 7.51. 0.00131. It's about 0.00984 atmospheres. 0.00984 atmospheres. All right, so what we have pi here, our osmotic pressure. I need to get my bearings straight here. Okay, we got our osmotic pressure. We have R, we have T, and what is, oh, by the way, what is M here? I don't think I mentioned M. Okay. M is molarity, and what are the units of molarity? That's molality. We're talking about molarity here. Mole solute liters of solution. Very good, Eric. Good job. All right, so pi equals MRT. Okay, so know this for the exam, okay, those units. Okay. All right, we have 0.00984 atmosphere. Okay, big M is moles of solute over liters of solution. Okay, what is our liters of solution? 10. Okay, let's go ahead and convert that to liters. How will we convert that to liters? Okay, we will divide by 1,000. Okay, divide by 1,000. So this liters of solution is 0.010 liters. Okay, so that's M. Okay, R is R, which I'll give you on the exam. 0.0821 liters atmosphere per mole Kelvin. Okay, T is temperature, and our temperature here is, what is our temperature? Okay, 25 degrees C, and what's 25 degrees C? Okay, I'll add 273 to get it to Kelvin. Okay, so again, this is like plug and chug, plug and play. Kelvins cancel, liters cancel, atmosphere cancel. Like before, like our previous problem, we'll solve for moles of solutes. Okay, so that's going to be 0.00984 atmospheres. Times 0.010 liters, okay, divided by 0.0821, okay, divided by 0.0821, 0.00984 times that 0.01, divide by the red, which is 0.0821. Okay, so this is going to equal to moles of solute. Okay, so 0.00984 times 0.081. Divided by 0.0821, so I'm getting about 0.011 or 0.00120. Okay, we'll do that.
Wait, and what is the 298 Kelvin do then?
120 moles. Okay, this is our moles of hemoglobin, which is our solvent. Solute. Go ahead, yes? Sorry.
Then what is the 298 Kelvin do then? Do they cancel out somewhere?
Yeah, the Kelvin cancels out with the units of R.
Oh no, because I was thinking like the mole solid one, you didn't put in like the,
Oh wait, did I do something wrong? Maybe you're right here.
Yeah,
0.04.
that was right there. I wanted to,
Oh, I need to divide by the 298. Yeah. Oh, thank you, Bailey.
Exactly, that don't look right.
Good call. All right, thank you for that. I did it on purpose so you can catch it. 0.00984 times 0.010 divided by parentheses 0.0821 times 298. Close those parentheses. This should be our final answer. 4.02 times 10 to the minus 6 moles. Okay, thank you again. Okay, provided I did this correctly. 4.02 times 10 to the minus 6 moles of solute, which is hemoglobin. All right, finally, our molecular weight is grams over moles. So we have how many grams here? Yes, very good. We have 0.263 grams. So we'll take that 0.263 grams and divide it by this many moles. Okay. Oops, sorry. .263 grams. Let's just do this here. I'm getting about 65,422 grams over moles. Okay, so this is our answer. So that is a wrap on Chapter 12. This ends the material for the exam. Just some take-home points. All right, so here are our 4 colligative properties and their corresponding equations. All right, so if you have something that's ionic, let's go to the next page here. If you have an ionic solution, it's a little different. Okay, of electrolyte solutions. So by electrolyte we mean ionic. Okay, it's the exact. Everything is the same, except you have to add multiply by this Van Hoff factor. So I won't test you on this, but the ions provide some activity as a solute. If your solute is ionic, the ions have an activity or conduction, and you have to multiply it by this factor. Okay, and your boiling point gets affected by the ions, and your freezing point gets affected by the ions. Your osmotic pressure gets affected by the ions that are in solution. Okay? So it usually is the number of ions that forms your I. Okay, so as an example, let's say your solute was not glucose. Okay, let's say your solute is NaCl. Okay. If your solute is NaCl and our solvent is water, okay, it's not just solute and solvent, okay? Because what happens is that this is solvation, ion dipole. So here, the sodium chloride in water gives you 2 ions. and those two ions have an effect on your boiling point and freezing point and osmotic pressure. It's called activity. If you look at your textbook, the ions have an activity. So sodium chloride gives you how many ions? One ion, two ions. Okay, so if your solute is NaCl and your solvent is water, you have to multiply it by the Van Hoff factor, which would be about 2. Yeah, 1.9, which is about 2. Okay. Let's look at the one below. Let's say your solute is iron chloride, iron 3 chloride. This too is also ionic because in water it gives you Fe plus 3 and 3 Cl minus, not 1, not 2, but 3 Cl minuses. So how many ions do we have here? 1 plus 3, 4. Okay, 4 ions. So those 4 ions, as your solute, affect your boiling point, affect your freezing point, they affect your osmotic pressure. They call it activity. They have some activity. So the Van Hoff factor, or I, would be about 4 here, but actually it's about 3.4. Okay? So you have to multiply it by this factor I, if it's ionic. Okay? If your solute is ionic. Now, if your solute is covalent, like glucose or urea or ethylene glycol, you just go by these equations. Okay? But if it's ionic, you have to multiply it by a factor that takes into account the ions and their conduction, because they conduct. Okay? And that's called I, which is the Van Hoff factor. Okay? Because the solute that's ionic gives rise to ions, okay, in the solvent. Ions. So you multiply it by that factor to take into account ions. Okay, that's called an electrolytic solution. Okay. So as far as test is concerned, it's just, we'll do this step here. Okay. Non-electrolytic, no ions. All right, and the rest are some practice problems that you can do at home and check your answers with mine. Okay, so
basically, like that part where it's just like review the 4 main calculated solutions, all that there. That's what we got to mainly study.
yes, and I'll give you the equations. You're welcome. All right, any questions, comments? All right, so maybe for the next 20 minutes or so, we'll go over the exam. So I have a practice test here, so let's go ahead and start that. You'll have similar types of questions on the test. So we'll do half of that for 20 minutes, and then we'll finish it up on Thursday. So we'll have our test next Tuesday. And the way my system works is the quiz is also due the same day as the test. So quiz 1 will be due on Tuesday as well.
So where are the quizzes located again?
They're on campus. I went over that on the first day. That's okay. Or if you want, you can make that your drop also. I'll drop 1 quiz. Okay? So there's about how many? 3 or 4 computation problems, and there's some short answer. So let's first do some computation. Problems. All right. So similar to the exam, maybe just some different numbers here and there. So calculate the new vapor pressure exerted by a solution when 10 grams of sucrose is poured into 200 milliliters of water at 25 degrees C. The vapor pressure of pure water at 25 degrees C is 23.76 millimeters of mercury. Back of the hand calculation, the density of water is about 1 gram per mil. Right, so here's the equation that you'll be given. The vapor pressure of pure water at 25 degrees by itself, it's also known as neat, totally by itself, is 23.76 millimeters of mercury. So this will be 23.76 millimeters of mercury. Okay, so this X here is what's called the mole fraction. Okay, mole fraction with the solvent at the numerator. Okay. Mole fraction. All right, so this is a fraction, but in this case, because it's mole fraction of the solvent is in the numerator. So which brings me to this question: what is the solvent and what is the solute? Solvent is water. Okay, you can 99% guess it will be water. And what will be our solute? This sugar sucrose. Yes, that's correct. All right, so it's saying mole fraction of the solvent. That means solvent in the numerator. Let's put this into moles. Okay, so this is mole fraction solvent. Okay, so we have 200 mLs times 1 gram per mil. The molecular weight of water is about 18.04 grams per mil. Yes. Okay. 1 mole of water is 18.04 grams per mil. So 200 divided by 18.04. 11.086 moles of water. Uh-oh. I did it. I killed the calculator. Oh, no, I didn't. Okay. So 200 divided by 18.04. 11.086 moles of water. And so let's calculate the mole fraction of this. Okay, mole fraction of the solvent, but what is the moles of solute? Okay, so we have 10 grams of sucrose, C12H22O11. Okay, 1 mole of this sucrose, C12H22O11, contains how many grams? Okay, so carbon is how much? 12.01, but we have 12 units. Plus, how much is water? About 1.01, we have 22 units. Plus oxygen, how much is oxygen? 16.01, and we got 11 oxygen atoms. So we sum up all those, getting about 342.45 grams in 1 mole of sucrose. Divided by 342.45, get about 0.0292 moles of this. Okay, so we have our moles of solute, we have our moles of solvent. Okay, we'll do the mole fraction of the solvent. Which gets in the numerator again? And what is that number? Okay, very good. Thank you, Jacob. And what goes in the denominator now? Both? Yes, both. Okay. 0.09292. Okay, so this is our mole fraction. And what is the vapor pressure of water neat or by itself? Okay, 23.76 millimeters of mercury. All right, so we'll take this times this and divide it by that sum, and this should give us our final answer. Okay, so this is given to us in the problem. This is the mole fraction solvent divided by solute solvent. Remember, the denominator contains the whole thing. So 11.086 times 23.76. Okay, divide this by the sum. Okay, sum, which would be 11.086 plus 0.0292, 23.70 millimeters of mercury. Okay, it went down, but it didn't really go down by much. Okay, it went down from 23.76 to 23.70. But as we know, vapor pressure goes down. Okay, by adding 10 grams of sucrose to pure water, the vapor pressure at 25 degrees goes down from 23.76 to 23.70. All right, so this is our answer. All right, so a problem like this on the exam, make sure you're confident and comfortable enough to do it. I'll probably just change the numbers here and there. Okay? And this equation will be given. Same problem, different numbers is what I'm saying. All right, how about this one here? The molar enthalpy of vaporization of diethyl ether is 26 kilojoules per mole. We'll also call that delta H vape. And its normal boiling point is 1 atmosphere at 34.6 degrees C. What is the vapor pressure of this molecule at room temp at 65 degrees? We can remove room. Okay, we'll just remove that at temperature 65 degrees C. What is the vapor pressure of diethyl ether at temperature 65 degrees C? All right, not room temperature, so that's a mistake on my part. All right, so this is plug and play. Okay, plug and play. We have 1 atmosphere. The vapor pressure is 1 atmosphere is at a temperature of 34.6 degrees C. We've increased the temperature to 65 degrees C. And we want to know what is the new vapor pressure. Okay. By the way, 1 atmosphere means normal pressure. Or normal boiling point means pressure is 1 atmosphere. All right, so we have natural log of P1, we'll call that 1. P2 is what we're trying to solve for. Delta H vaporization, we will convert that to joules per mole, okay, because R is in joules. Okay, so that's going to be 26,000 joules over a mole. This is delta H vaporization. Okay, R in the denominator is 8.314 joules over a mole Kelvin. Okay, this is R. Okay, this is 1 over T2, so T2 is 65 degrees. We need to convert it to Kelvin. So what is 65 degrees in Kelvin? 65 plus 273. About 338 Kelvin. (273 plus 34.6). 307.6 Kelvin for T1. Okay, does anybody have any questions with the setup? Okay, I'm just putting everything is. Just don't forget to convert that to 26,000. Multiplied by 1,000 to get it to joules per mole. And R is R. And don't forget to convert the temperatures to Kelvin. So I put everything in here. We don't put units inside the natural log. Okay. All right, so let's do this in one shot in our calculator. Okay. All right, everybody ready? Okay, see if we get the same answer on our calculator. Okay, first I'm going to do this, the fraction. 1 over 338 minus 1 divided by 307.6 times 26,000 divided by 8.314. Okay, I'm getting negative 0.9144. Oh, yes, okay. Divide by R, yeah, okay. Negative 0.91440, I guess. That's what I'm getting when I do this whole big chunk of math. And then that is equal to natural log 1 over P2. So now we'll do the inverse log of both sides. So we'll take E of both sides of the equation. Okay, so E to the power of natural log of 1 over P2 equals E to the power of negative 0.91440. Okay, so 1 over P2. What's E to the power of this number here? So on our calculator, we're going to do inverse natural log. Okay, or whatever your calculator may be. Okay, just make sure you know how to do inverse natural log. On this calculator, it's going to be second natural log, okay, and that number. Okay. Does everyone know how to calculate E, which is E to the power or inverse natural log? So enter that. We're getting 0.4008. So make sure you know that before next Tuesday, 0.4008 or so. So that means P2 is going to equal to 1 divided by 0.4008. What is that? 0.025? Let's see here. 1 divided by that. I'm sorry. 2.50. 2.50. And let's put our units. What are our units? Atmospheres. Actually, it makes sense. You raise the temperature, you would expect more vapor pressure. Yeah. Right. So you expect more vapor because you've raised the temperature, so the vapor pressure should go up. So this is the answer I'm getting. All right. So you'll do something like this, similar to the exam, similar pipeline. Okay. You raise the temperature, more vapor, so more vapor pressure. Okay, any questions or comments on this? Okay. Like I said, kind of a similar problem, just different numbers. In our last 5 minutes or so, let's see if we can knock this out in 5 minutes. Boiling point and freezing point. Because we did a problem already like this, so hopefully everyone will get this correct on the test. Okay. So what is the new freezing point and boiling point? Of an aqueous solution containing 4.5 grams of glucose, we put it in 150 milliliters of water. So what is our solute? Glucose. We just did a similar problem like this, I think 20-30 minutes ago. What is our solvent? Water. Okay. And so let's see here. Let's do 4.5 grams of glucose. Let's convert that to mole. Let's see. M's is moles of solute over kilograms of solvent. So what is our moles of solute? 4.5 grams of glucose. Carbon is about 12.01. We have 6 units, plus hydrogen is 1.01, we have 12 units, and then oxygen is about 16.01, and then we have 6 units. About 180.24 grams. Okay, so 4.5 divided by that number. Getting about 0.0250 moles of our solute glucose. Okay, what is kilograms of water? 150 milliliters is about 150 grams. The density of water is about 150 grams, okay, because of our density here. So 150 milliliters is about 150 grams, and which is about 0.15 kilograms. Yeah, but I'm converting it to grams using the density. The density of water being 1 gram per mil is kind of a backhand number that I always memorize. Yeah. Right, so our molality is 0.0250 divided by 0.150. 0.167. Molal. Just double check my calculations. Okay. All right, let's do the boiling point and freezing point. Okay, KB is 0.52 degrees C over M. M is 0.167. And we'll just do the freezing point too. We'll knock both of them out. KF is 1.86 degrees C divided by M. And our molal is 0.167. So we'll add some 4.5 grams of glucose to water, and our boiling point, we'll do boiling point first. We'll go up by 0.089 degrees C. So our new boiling point will go up by how much? About 100.08 or 100.1?
You don't need to know anything personal like that. That's too much. That's too much. They don't need to know like actual stuff.
87. Okay.
Oh yeah.
So yeah, about 100.087, which is about 100.1. And our new freezing point will go down by 0.31 degrees C, which means our new freezing point is 0 degrees minus 0.31 degrees. So it's going to be about minus 0.31 degrees C. So our boiling point goes up by about 0.1 degrees. Our freezing point goes down by 0.3 degrees if you add glucose to water. All right, I will see you all in lab if you have the Tuesday lab. All right, so that type of question is on the exam. On Thursday, we'll finish this up, do some of the computation problems, do some short answer, and then we'll start chapter 13. Okay, make sure you turn in your homework 11 and 12. Okay, I'm just putting in the 10 points, but make sure you upload that in.